Hey everyone, welcome back. In today's video, we're continuing the discussion on velocity. This time, specifically, I want to look at the constraints in the problem, and then I want to consider the effects of velocity on those constraints. So, what do we want? We want the velocity constraints. So, what's the approach for finding velocity constraints? We're building a recipe, right? We're building a procedure that we can use on any problem to solve the dynamics for that problem. So step number one is going to be position and orientation. Step number two is going to be constraints and degrees of freedom. Next, let's do linear and angular velocities. And then after that, we will do the velocity constraints. So when I say velocity constraints, here's what I mean. Mathematically, it's as simple as taking your original constraint equations and taking the derivatives of them. Congratulations. Those are the velocity constraints. The deeper meaning behind it, or the purpose of the velocity level constraints. Consider what is the purpose of the original constraints. These equations, they allow you to solve for one generalized coordinate in terms of another. And in that way, we can define relationships between dependent and independent variables. In this case, this is going to define the relationship between independent and dependent speeds. Now, when I say speed, the word speed is, in this case, it's specifically different than velocity. These are not the same thing, speed and velocity. So velocity is a vector and speed is a scalar. We could think of it as, for example, theta dot by itself. Theta dot is a speed. If we had something where omega equals theta dot around some z-axis, okay, now it's a velocity because now it's a vector. So, in this case, we won't use this terminology so much in this class. You don't have to know this, but this is usually called generalized speeds. So if you're generalized coordinates, you take the derivative of those, you get your generalized speeds. So these velocity constraints allow you to define the relationships between the generalized speeds. Okay, so here's the problem we're going to do. We're going to do this procedure on it. Some of these things, I expect that you're comfortable doing them, so we'll move quickly. The constraints and the degrees of freedom, again, we've spent some time doing this. And there's nothing inherently new in this problem, so we should be able to move through this pretty quick. And linear and angular velocities, if you've watched those other videos, you should be good there. So most of this is going to be a review. We're just going to do it on a new problem, right? We're going to do the whole process. Okay. So let's talk about the mechanism and what this thing is doing. Okay, so what have we got? We've got two disks, and they're connected via a Pulley and belt situation. So we've got this belt that has been strung around this pulley system. So we've got a small disk. Small disk is going to drive the large disk. Now, what this means this circle inside of a circle, if we drew it in 3 dimensions, it would be a disk with another disk attached to it, like this. And they're rigidly attached. So this is actually all one body, just looking at it from the side. So in this inner radius here, this is where your pulley system is. This is where the belt is attached. So the belt is coming off of that inner disk like this, winding around the back. So on the outer portion of the disc, this is where we have a coupler that has been attached, and then we have an output crank. So the purpose of this mechanism is to generate some motion in the coupler and the output crank. It could be that maybe there's a tool at this joint, and we're attempting to control the position of this tool. There's all kinds of reasons we could string this thing together. So let's roll through the intuition portion of the problem. Just looking at it, how many bodies are there and how do they move? There's a little disc, there's a big disc, there is a coupler attached to the big disc, and then there is the output crank. So four bodies, and they're all going to rotate, and we're not going to need any translation variables. So in this case, we're going to have theta, 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 and theta. So 1, 2, 3, 4. So for generalized coordinates, theta 1, theta 2, theta 3, theta 4. How many degrees of freedom? Well, if we were to reach out and we were to spin this little disc by hand, it's going to make the big disc turn, right? It's the constraint between them. And imagine actually that we cover up the little disc. What does this system become? Consider that we could just as easily have built this system using another rod, right? If I replace this big disc with just a rod, we can see that this is now a 4-bar linkage. So kinematically, meaning as far as the motion of this is concerned, if you were only looking at the output crank, for example, and the only thing we were looking at is how the output crank moves back and forth, it would make no difference if this disc were here or if it were just a rod. Now, it will make a difference in the mass of the disc and in the inertia of the disc and how much torque it takes to get this thing turning. That will make a difference. But as far as the kinematics, just the motion itself, it's not going to make a change. So this part of the mechanism, covering up the little disc, this is just a 4-bar linkage. And we know that the 4-bar linkage has 1 degree of freedom. And if I tack on the pulley, well, I've added an additional angle, but I've also added an additional constraint equation. So our expectation is this system has 1 degree of freedom, and it does. So let's knock out the position and orientation parts of this. Okay, we know that we need an inertial reference frame. I'm just going to do that to save some time. We know that we need a series of points. Let's do point A, B, C, D. I'm going to put point E on this guy over here. All right. How about frames? Okay. Let's call them bodies A, B, C, and because we put point E on this thing, let's call this one body E. We can do that. We can name these things anything we want. So point E, body E, frame E. All right, how do we want to select these coordinate frames? Well, we know there's some constraint with this 4-bar linkage. We're going to do a vector loop. Let's pick the frames such that it's easy to do the vector loop. Let's say that this blue that I've already drawn, that is your X, B axis. So here's YB, or sorry, YA, A. Okay, XA, YA, there we go. B frame, let's just go from B to C. C frame, let's go C to D. And I'm just going to do this to be, save a little time. Please do not do that on homework or an exam. E-frame, does it actually matter how we select E-frame? This disc just spins and there's no real points of interest on this disc, so there we go. E-frame. All right, let's do position vectors. So P into A. Oh, we didn't put point in on it, that's okay. There you go. There's your point in. So P into A now is 0. Let's go P into B. All right, so P into B, we're going from the middle of the big disc to the outer edge of the big disc, where this coupler attaches. That's a fixed distance. We could, if you want, you could use r's, radii. What I'm going to do is I'm going to use L for this one. So this is L1 x hat A. And let's, we know that we're going to do a vector loop. Let's just go ahead and create the pieces of the vector loop for B and C and get that out of the way. So A to B, the position vector from, let's see, we went into B, so we need B to C. This one's L2 x B. Let's do P, C to D. That's L3 x C. And we need to know where this disk is. Even though it doesn't move, it's a part of the problem. You need to be able to track these things. So P into E, it's not moving, so fixed offsets, we're going down and we're going left. So negative L4 x hat N minus L5. L5 y N, there we are. Okay, all of that's pretty simple. We have 4 frames, A, B, C, and E frames that we would have to define rotations for. I'm not going to do that on this problem. We've done it so many times. I think y'all are okay. So I'm just going to write down at the bottom, and this is my personal shorthand for just this, for this lecture. Again, do not do this on an exam. Let's say, yeah, okay, so your rotation about Z, theta 1. Okay, so this is just some quick shorthand. The rotation from N to A, which is, we've defined it numerous times. It's a rotation about a shared Z-axis. The variable is theta 1. So the rotation is a function of theta 1. And we could do the same thing for all the others. We could say R into B is a simple rotation around a shared Z, and the angle there is theta 2. Notice we're going from N to B, which means it's an absolute angle. N to C is a rotation about Z, theta 3, etc. Okay, so E frame then is going to be theta 4. All right, and you can just write that one in your notes. Okay, this takes care of positions and orientations. Let's do the constraints. I redrew it just to make it smaller, save a little room. Okay, we need the constraints for this thing. So we can see there's a belt and pulley system, and there's a 4-bar linkage, so we're going to have to do a vector loop. So let's do the belt and pulley, get that thing out of the way. It's connected to this inner radius of disk A and just the radius of E. So specifically for this one, I'm going to use RA and RE to call out those radii. So this is RA theta 1. Theta 1 was associated with the rotation of A frame, and then RB theta 4 was E frame. Okay, and that's literally it. They rotate in the same direction, so there's a positive relationship between these two. Okay, put a little box around it. There you go. There's your belt and pulley constraint. Next, we need to do a vector loop, and we've called out a lot of those already. So if we're going to do the position vector from N to N, we know that this is distance is 0. So we're going to do L1xa, L2xb, and L3xc. So that gets us N to B, B to C, C to D, and then we need to go from D back to point N. If we don't know anything about the specific dimensions, it's safest to assume that these things are not aligned. So let's say we got to go down and we got to go left to get back. So we already did L4 and L5 getting to point E, so this is now 6 and 7. So minus L6 and minus L7. Okay. So constraints. You've done several constraints by now. Finished the homework. We've done problems like this repeatedly. So what's going to happen is we're going to take this vector loop, we're going to dot it with x hat n, and we're going to dot it with y hat n. If you're still struggling with this, you can manually replace each of these with their definitions from the rotations. If you feel comfortable just going right to it, do so. This is L1 cosine theta 1, L2 cosine theta 2, L3 cosine theta 3, and then minus L6. L1 sine theta 1, 2 sine theta 2, L3 sine theta 3, and L7. Okay, draw a box around these. These are your constraint equations. Okay, next. Now, if you're working a problem and the problem says derive the constraint equations, everything that we've done up until now has been absolutely necessary. There is a little flexibility in whether or not you want to individually go find the linear velocity of points B and C and D, etc. What you'll find is they'll actually come out of this vector loop, because consider this vector loop is actually all of the position vectors, right? Which means if we take the derivative of the vector loop, it's like you're adding all these little individual velocities. So what I would like to do though, I would like to list out the angular velocities just so we have those recorded. I can actually fit it in right here. Okay. So just so we have them, omega NA, this is theta 1 dot, ZA, omega NB is theta 2 dot, ZB, into C is theta 3 dot, ZC, and omega into E was theta 4 dot, Z, E. Okay. Got that knocked out. All right. So at this point, we've done everything that we need to support us going after the velocity constraints. Now, on an exam, just going to throw this in here and I'll talk about it again later. On an exam, I will be very specific about what I want you to do. So there is no ambiguity about do I need to write these down or do I not. I will list explicitly do this, do this, do this, do this. On this problem, do we explicitly have to do this? No, by all means, you could have worked this thing without writing it down. When you're in my class, right, I just ask that you do this so the grader sees it and he gives you your points. So we've gotten all of this. We want to go after the velocity constraints. What do we do next? Well, let's go ahead and knock out the Pulley constraint, get that out of the way. This is the original constraint. We want the velocity constraint. That means you take ddt of this thing, by which I mean take ddt of both sides. If that kind of throws you, if you're not sure about taking ddt of both sides, consider that you could put these on the same side of the equal sign. There you go. Now take ddt of it. Okay, you get the same thing. So we take ddt of this equation. What's going to happen? We can distribute the ddt so that both of these terms individually get it. We can do product rule expansion on this. And of course, these RA and, oh, I wrote RB. Sorry, habits. It's RE, okay. Product rule expansion, the radii are constants. These scalars, right, are not constant. So we're going to end up with RA theta 1 dot equals RE theta 4 dot. There you go. There's your velocity level constraint. Doesn't get easier than that. All right. So those are out of the way. Next. So we wanted the velocity level loop constraints. So what do? You have actually a choice at this point. You can do one of two things. And again, it just depends on the problem and what is specifically being asked of you. If, for example, if I specifically ask for the constraint equations, that's these scalar equations. You have to put them in scalar form. We could directly take the derivative of these equations, and we will. That's what we're going to do on this one. But there is something else we could have done, and we can do that one too, just to prove that we get the same thing. The other thing that we could do is we could take the original loop, x in, no, that was a, x a, okay. L2 x b, L3 x c, 4, 5, 6, and 7. Okay, so this is the original vector loop. We dot product it to give us these. You have your choice. You can either do the dot product and then take derivatives, or you can take the derivative of the vector equation and then do the dot products. And depending on what you have to do in the problem, that might end up saving you time. So let's do both of them, actually, and let's prove that you get the same answer. So I'm going to take the derivative, and just for space, I'll do it above and then below. So ddt of equation number 1. Well, this thing's still equal to 0. So imagine that we did ddt of this whole expression. You can linearly distribute the ddt, so each of these terms get their own ddt. So this is like writing ddt of, and my blue is crap. This is like writing ddt of L1 cosine theta 1 plus ddt of L2 cosine theta 2 plus dot, dot, dot. All right, so this is what I mean when I say linear distribute. Each one of these individually gets the ddt. Now, what's going to happen when we take those ddt's? Product rule expansions on all of these. The L1s are all constants, so these are all going to go to 0. Each of these are conveniently cosines, so ddt of cosine is going to be a negative sign, and then don't forget the chain rule. And then the way that we set the frames up makes it very conducive to this process because it was x-axis, 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 so cosine, cosine, cosine. We saw in the other video with the 3D problem that sometimes it's going to be cosine, and depending on how you set it up, it could be sine or negative sine or all kinds of stuff. Once you've done these several times, when you just look at the problem, you'll get a feel for how to set up the frames to make this math come out very easy. So what's going to happen when we take ddt here? Like I said, distribute, product rule, chain rule. So L1 theta 1 dot, and this is now negative sign, so I'll put the negative in front. Negative L1 theta 1 dot sine theta 1 minus L2 theta 2 dot sine theta 2 minus L3 theta 3 dot sine theta 3. Now what happens to the L6? L6 was an offset, it's a constant, it goes to 0. Okay, so that's it. That's ddt of the first equation. How about ddt of the second? So this is still equal to 0. Don't forget the 0. 0 is important. It's an equation, not an expression. Linearly distribute the ddt. Do product rule expansion. These lengths are all constant. The L7 at the end is constant. ddt of sine is cosine. And chain rule gives us L1 theta 1 dot cosine theta 1, L2 theta 2 dot cosine theta 2, L3 theta 3 dot cosine theta 3, excuse me. Okay, so we've got all of that done. What happens if we go at it just on the vector form? Same thing's going to happen. We're going to do ddt, right? And we're going to linearly distribute the ddt. And the L6 and the L7, those are going to go to 0. So what's going to happen to the ones in the middle? We've already got all of this, so I'm going to erase it. And the blue didn't show up very well anyway. Sorry. Okay. So, DDT of this guy now. So DDT of P and N, this is still equal to 0. Okay. So DDT of, we linearly distribute this thing, so L1 x at A plus dot dot dot. All right. We've done this. This is now just a bunch of linear velocities, right? So you do product rule expansion on this. You get two terms, DDT of L1 x at A and L1 DDT of XA. This first term is going to equal 0. L1's a constant. And of course the second term now, we're taking DDT of a moving frame, which means we can replace this using transport theorem. Transport theorem has the same form every time. It's the angular velocity of the frame you're taking the derivative of cross some other vector. What vector do we use? Well, we're going to use L1 XA. So in this original vector loop, we're going to repeat this process 3 times. We can see that. We can see 1, 2, 3. So each of those 3, we could do the product rule expansion. One term is going to be 0. And then we're going to have a transport theorem come out of it. So let's just jump right to the transport theorem. Let's write this down. Omega into A cross L1x at A plus omega into B cross L2xB and then plus omega into C cross L3xc. Okay. So we've already defined the angular velocities. This is, oh yeah? Get up here. Theta 1 dot ZA. This one is theta 2 dot ZB and theta 3 dot ZC. Okay. So we can resolve those cross products. You can use whatever method you want. I'm just going to do multiply the scalars together, L1 theta 1 dot, and then Z cross A is Y. Plus scalars L2 theta 2 dot, Z cross X is Y again, and then plus L3 theta 3 dot Y C. And then the last terms are 0. Now, what this is doing is we took a position vector P into B and P B to C and P C to D. And what we got out of taking the derivative was, first of all, the absolute velocity of B, because this position vector started at point N, and then we got the relative velocity of C with respect to B, and then we got the relative velocity of C with respect to D. D with respect to C. Okay, we are gonna have another video on relative velocities, and it's not particularly difficult. It's just showing mathematically what we already know intuitively, which is the example. If you're in a moving car and you look at somebody else in a moving car, you observe a different speed compared to if you were someone standing on the side of the interstate looking at both cars drive by. So really what we've done is we've taken the velocity of B and we added to it this relative velocity, and then we've added to it this relative velocity. So when you take these 3 things and add them together, what you get is you get VD. So VD is VB plus VB to C plus VC to D. And what is VD? Go back and look at the diagram. D was the other pin joint. VD is 0. And hey, that's what this says, right? So taking these three things and adding them together, they should equal 0. So in this case, intuition and math, they're all lined up. Okay, so what can we do at this point? At this point, we can do dot products. So if I call this one, let's say this is equation, let's see, we have 1 and 2. Okay, so we're looking at 3 now, equation 3. So if we take equation 3 and we dot it with x hat in, if we take equation 3 and we dot it with y hat in, so go back to the definitions of rotations and look at how we defined YA, YB, and YC. Recall that YA, for example, is negative sine x hat in plus cosine y hat in. So what happens when we take the dot products? Well, imagine that each of these have been replaced with the definition of rotation. When you dot with x hat in, you're going to get the negative sign. When you dot with y hat in, you're going to get the positive cosine. So these come out to be L1 theta 1 dot cosine. Oop. Nope. Negative L1 theta 1 dot sine theta 1 minus L2 theta 2 dot sine theta 2 minus L3 theta 3 dot sine theta 3. Okay. And then here's the cosines. L1 theta 1 dot cos theta 1, L2 theta 2 dot cos theta 2, and L3 theta 3 dot cos theta 3. Okay. So that was a long walk, but it shows that the order of operations on your derivatives and your dot products doesn't matter. If you want to do your dot products first and then take derivatives, be my guest. If all you're going for is the final product, if the only thing you have to do is just generate, let's say acceleration level constraints, which we're going to do, and you don't explicitly have to give the other constraints, which would be kind of weird, and I wouldn't ask you to do it on an exam, but just recognize you could make the position vector loop, take the derivative, and then you can actually just take the derivative of this directly as it is. And we will do some mini examples at the acceleration level, but just FYI, in this problem we're looking at specifics, right? This is the specific length and angular velocity of that particular body, right? And it's in that particular direction. This whole process, though, can actually be generalized, and I do not expect you to be able to do this on an exam or a homework or anything, but just consider that if you have a position vector P and A, if it exists, we don't have to know what it is. I can tell you that VA is omega NA cross P and A, assuming there is no translation variable. If there is a translation variable, that's fine too. We draw it this way, or we write it this way. We just say the velocity of A in the A-frame, which means if you're taking the derivative of a position vector in that same direction, then it's like the frame's not moving. The example that we talked about was you're standing in the middle of the merry-go-round, and there's the cat on the merry-go-round with you. From your perspective, this cat walks in a straight line. From your friend's perspective over here, the cat is walking in a spiral, right? So the component of the cat's velocity that is moving in the straight line, it's like the q dot term that goes here, and then you have your translation here. You can actually take the derivative of it in this form, and you're going to get some things that look like this. You're going to get omega dot cross a position vector, and you're going to get omega cross the position vector. And there's some more things there too. And we'll talk about it when we get to the acceleration level. And that's kind of what I did here in this manner, right? I just said omega cross the position vector. Well, hey, that's what transport theorem is. In the more advanced problems, understand that we don't actually care what P and A is. P into A, it could be 0.01 and negative 15 and 6.28, right? And we just take this and we map it to some algorithm that just reads whatever the data is, the dimensions, and it reads whatever this is, and it automatically performs a cross product forward and just adds it up. So that's how all of this ends up being done on a very large project. If you're interested in that, if you want to be able to work this in a more formal way without worrying too much about the specifics, we do, UTA does offer the Advanced Dynamics class with Dr. Bowling, so you could always take that one. Okay, so that's it for this video. We're gonna come back over the next week and a half or so with, we're gonna do all the other constraints. So what have we done? We did loop and we did pulley. Okay, so we need to, we still need to do velocity constraints with gears and rolling and ropes. And of course there was that, you know, that geometric case. If you just have something else going on, I know, right? You just take derivatives of those as well and do the best you can, because sometimes they get nasty. All right, so we've got some more velocity constraint videos coming. We've got a relative velocity video, and then after that it's acceleration. So, okay, that's it for tonight. I'll see you next time.